October 2025, ESA released its first official images of 3I Atlas, an interstellar object moving through our solar system with a trajectory that should not exist. They look ordinary at first, a blur of light, a coma, a trail of dust, but beneath those pixels lies a problem no agency has yet explained. If the ESA photos are real and unaltered, then what they show does not fit with any known cometary model, and the question changes from "what is it?" to "why are others silent?" Before we go further, like and subscribe, tell me where you're listening from, and the time on your clock. Now let's unravel what these images actually mean. It began as a single image on ESA's official portal, a faint white blur against the backdrop of deep space. Captured by the Cassis camera aboard the ExoMars Trace Gas Orbiter, it shouldn't have been possible to see this much, this clearly, from that far away. The camera wasn't designed for astronomy. Its job was to photograph the Martian surface, mapping sand dunes, mineral streaks, and the subtle colour shifts of rock across Jezero crater. But on October 3rd, 2025, it was turned toward the sky, and what it recorded made even seasoned scientists pause. At first glance, it looked like nothing, just a faint fuzzy point surrounded by static, but after calibration and motion correction, the object resolved into a distinct coma, a cloud of gas and dust several thousand kilometers wide. The official caption described it as a slightly fuzzy white dot moving through the frame. That's the kind of understatement used when something extraordinary happens and no one's ready to say it out loud. Because here's the problem. The brightness, the color, and even the motion of that dot all break the rules of ordinary comet behavior. The Cassis instrument was operating far outside its designed parameters. 3I Atlas was nearly 30 million kilometers away at the time. Under those conditions, the nucleus should have been invisible. Even the coma should have been too dim to register in 5-second exposures. And yet, not only did Cassis capture it, the glow was measurable, stable, and strangely uniform. That uniformity suggests either unusual material composition or controlled emission, neither of which fits a random chunk of interstellar ice. ESA's own internal memo, later summarized in their public statement, mentioned unexpected stability across frames. In plain terms, that means the object's brightness didn't flicker. Most comets pulse as they rotate, their surfaces flashing sunlight in uneven bursts. 3I Atlas didn't. It remained steady, like an artificial beacon, holding luminosity with mechanical precision. Then there's the issue of geometry. Amateur astronomers who processed the raw data noticed that the coma wasn't perfectly spherical. It showed symmetry, subtle but real, almost polygonal when contrast was increased. ESA didn't confirm that, but they didn't deny it either. The official release skipped over shape entirely, focusing instead on how difficult the observation was, how remarkable it was to capture anything at all. That's the kind of language that conceals more than it reveals. If you trace the imaging logs, Cassis performed 5 exposures in sequence, spaced roughly 90 seconds apart. The object moved exactly as predicted except for a 3-second deviation in the midpoint frame. The kind of deviation you'd expect if the light source pulsed or reflected rather than purely emitted. That's subtle. But for interstellar observers, it matters, because reflection implies surface structure. Surface structure implies design. When analysts tried to match the brightness curve to known comet models, the numbers wouldn't fit. The reflectivity implied a surface 10 times brighter than typical carbonaceous material. Either 3I Atlas was composed of a rare reflective compound, or the light we're seeing wasn't just sunlight, it was emission. In other words, something active. ESA's scientists know how extraordinary that claim would be. That's why their report ends with a single sentence that feels more like a warning than a conclusion. Further analysis is required to verify the nature of the observed emission. In the cautious language of space agencies, verify means we saw something we can't yet explain. The image shouldn't exist not because it's fake, but because every variable says it shouldn't have been visible at all. A camera meant for dusty Martian hills somehow caught a structured light source 30 million kilometers away, and if Cassis truly recorded what those pixels suggest, then either we've misunderstood how comets behave in interstellar space, or 3I Atlas is the first object ever photographed that's following the laws of something other than nature. In space science, silence is never neutral. It either means the data is still being processed, or it means someone doesn't want to talk about what the data shows. when the European Space Agency released their modest, almost apologetic images of 3I Atlas on October 7th, 2025, the expectation was that other space agencies would follow. They didn't. Not NASA, not the China National Space Administration, not the UAE's HOPE mission. 3 continents, 3 separate command networks, all equipped with instruments that saw the same object within the same 24-hour window. And all of them went quiet. At first, journalists called it routine. NASA was still crippled by the government shutdown that had begun on October 1st. More than 80% of its workforce was furloughed, including personnel at the Jet Propulsion Laboratory, the center responsible for managing Mars data streams. In theory, that could explain the delay. But even a shutdown can't mute the entire global scientific community. Data from Mars orbiters typically travels on autopilot through the Deep Space Network, uploaded and mirrored at multiple institutions across continents. It doesn't wait for press officers to wake up. If the feed had continued normally, the raw files from October 3rd would have appeared in NASA's open database within hours. Instead, the upload stopped cold. China's silence was harder to justify. Tianwen-1, the orbiter that had previously released more than 14,000 public images from Mars, suddenly produced nothing. Not a single image, not a telemetry update, not even a generic press note acknowledging the 3I Atlas flyby. This from a space agency that treats every opportunity for prestige as a chance to outshine its rivals. China's media has always been quick to boast about high-resolution mapping, rover milestones, or atmospheric findings. Yet when an interstellar visitor passed closer to Mars than any object in human history, state channels fell mute. The timing felt too deliberate to be coincidence. Then there was the United Arab Emirates HOPE orbiter, a mission that had built its reputation on transparency. The UAE often publishes its Mars data in near real time, in part to showcase its growing scientific capabilities. But their data portal showed a blank gap where observations from early October should have been. No notice of technical failure, no mention of scheduled maintenance. Just silence, the kind that only happens when someone chooses not to fill it. ESA's lone release made that silence even louder. Their statement opened by calling the observation a modest success under challenging conditions, and ended by promising further analysis over the coming months. Nowhere did they explain why other agencies hadn't spoken. Up. No coordination note, no cross-reference, no reassurance that the silence was normal. The omission was glaring, because in planetary science, international collaboration is standard procedure. When one agency observes something rare, the others usually confirm it. It's how credibility is maintained. But here, confirmation never came. Scientists who work in multi-agency missions understand that silence is often political. Raw data doesn't disappear. It gets classified. When multiple agencies go dark simultaneously, it usually means one of two things. Either the data contains national security, sensitive instrumentation details, or it shows something that no one knows how to interpret yet. Neither scenario bodes well for transparency. Behind closed doors, whispers started to circulate among planetary scientists. Some speculated that the images captured structural geometry within the coma shapes that shouldn't exist in natural outgassing patterns. Others suggested the problem wasn't what they saw, but what they didn't. The expected volatile signatures missing from spectral scans. Whatever it was, it triggered a coordinated pause across institutions that normally compete rather than cooperate. Publicly, all 3 agencies hid behind timing excuses. NASA blamed the shutdown. China cited internal data review. The UAE mentioned bandwidth reallocation, yet not one of them provided a new release date. As the days stretched into a week, the story of 3I Atlas became less about what it was and more about what no one was saying. For the first time in years, the global space community fractured along invisible lines of silence. ESA had spoken, but only softly. Everyone else held their breath. And somewhere in that collective stillness, people began to wonder whether the agencies weren't just withholding data. Maybe they were waiting for permission. When light passes through a prism, it tells the truth. Every atom, every molecule, leaves behind a signature, a pattern of lines so distinct that astronomers can read a comet's chemistry from millions of kilometers away. This is spectroscopy, the science of decoding light. For over a century, it has never lied. So when the spectra of 3I Atlas returned to Earth and refused to match any known template, the first assumption was simple. The data must be wrong. But it wasn't. ESA's ExoMars Trace Gas Orbiter used 3 spectrometers during the October observation campaign: Nomad, ACS, and Cassis, each designed to split light into its components and reveal what substances were being excited by the sunday. The expectation was textbook peaks of water vapor, carbon dioxide, and dust emissions, the fingerprints of an ordinary comet. Instead, the first composite spectrum came back with lines that didn't belong. Some were faint, buried in noise. Others were bright and stable, repeating across multiple instruments. The initial analysis showed strong nickel signatures but little to no iron, an inversion of normal cosmic abundance. In the cosmos, iron outnumbers nickel by about 10 to 1. That ratio doesn't flip. Ever. Scientists tried to explain it away. Calibration error, misaligned wavelength reference, thermal noise in the detector arrays. For 3 days, teams rechecked the pipeline. Nothing changed. The nickel remained, the iron stayed silent. That's when the whispers began. Maybe the signal wasn't from emission at all. Maybe it was reflection. If that were true, it would mean the object's surface was scattering sunlight in a highly selective way, something like a diffraction grating, engineered to favor certain wavelengths over others. Natural surfaces can't do that. Ice and dust reflect light broadly. Only structured materials, thin films, layered metals, photonic lattices create selective reflection bands. In laboratory optics, that's called spectral filtering. In space, it's never been observed from a natural body. The anomaly deepened when the infrared data arrived from ground-based telescopes. The James Webb Space Telescope observed 3I Atlas for 20 minutes during a window in late September. The spectral curve showed an unexpected dip around 4.6 micrometers, precisely where carbon monoxide emission should have spiked. In place of a smooth absorption valley, Webb recorded an abrupt cutoff like a signal being clipped. That kind of cutoff suggests interference, as if another material layer was blocking the expected signature. At the same time, an ultraviolet spectrograph on Mars Express picked up something else. Narrowband emissions near 280 nanometers, typically associated with ionized magnesium. Magnesium isn't rare, but the intensity was wrong, too sharp, too coherent. Some speculated it could be an artifact from cosmic rays. Others noticed that the peaks appeared at consistent intervals, spaced evenly like harmonics of a single underlying frequency. Nature rarely produces evenly spaced spectral harmonics. Machines do. ESA's public report used careful phrasing. The spectral data show features that require additional calibration to confirm or rule out instrumental sources. Translation: we saw something impossible, and we can't say that out loud. Privately, the data analysts began comparing 3I Atlas's spectra to historical baselines from 1I, Oumuamua and 2I divided by Borisov, the only other confirmed interstellar visitors. Both of those objects had normal cometary spectra, broad water, and CO2 lines, faint silicate dust. 3I Atlas didn't match either. Its nickel-to-iron ratio was inverted, its molecular bands partially suppressed, and its emission profile showed micropulses, slight fluctuations repeating every 4 seconds across multiple instruments. The synchronization was too consistent to be random noise. One researcher called it heartbeat data, a rhythm buried in the spectrum itself, subtle but steady. When cross-correlated between instruments, the pulses aligned. No known natural process could produce periodic modulation across independent detectors separated by millions of kilometers. Was it data compression interference? Possibly. But then, why would the pattern persist across 3 agencies and 2 different signal chains? By mid-October, the working theory split into 2 camps. The first insisted on a natural cause, surface crystallization, localized jets, or rotational interference. The second, smaller but growing, proposed something far stranger, that 3I Atlas might be exhibiting frequency-controlled emission, a phenomenon consistent with coherent light scattering, or even directed transmission. In plain language, that means the object could be sending something energy, data, or modulation. The ESA brief ended with a single, ambiguous note. No conclusive evidence of artificial modulation has been confirmed, but it didn't say it had been ruled out. For over a century, spectroscopy has been astronomy's most reliable witness. It showed us helium before we ever saw it on Earth. It proved the existence of exoplanets, black holes, and cosmic expansion. But 3I Atlas is testing that faith. Because when the light of a distant object refuses to obey known physics, you have two choices: question your instruments or question your understanding of the universe. And as the data keeps returning unchanged, fewer scientists are blaming the instruments. When ESA released the first calibrated frames of 3I Atlas, the public saw nothing unusual, just a faint white blur, the way comets have always looked. But to the astronomers who examined the raw color data, something immediately stood out. Buried inside the noise curves was a saturation spike in the green band, far stronger than models predicted. At first, analysts assumed it was a processing artifact, a byproduct of the camera's color filter array. Yet the anomaly persisted even in the unprocessed spectra. The coma of 3I Atlas wasn't white at all. It was green. Green comets aren't new. When ultraviolet sunlight strikes diatomic carbon, C2, or cyanogen, CN, both emit a greenish glow. Most comets display a faint tint for a few days near perihelion before it fades under solar wind pressure. But what ESA recorded was far beyond that. The green emission of 3I Atlas was measurable at 30 million kilometers a distance where other comets are still colorless. The intensity ratio of green to red light was nearly 5 times higher than expected. In technical terms, the G-band flux was overluminous. In everyday language, it was shining the wrong color for where it was and how much sunlight it received. Researchers at the Max Planck Institute for Solar System Research ran the numbers. The carbon emission alone couldn't explain it. To generate that much brightness, the coma would need a carbon abundance 50 times higher than any known comet, or a mechanism actively exciting those carbon molecules beyond solar energy alone. Some proposed an internal electrical field, a static charge built up by interaction with the solar wind, but the measured polarization didn't match. Others speculated about exotic compounds, chlorophyll derivatives, metal organic complexes, photoluminescent crystals. The chemistry quickly drifted beyond known space science and into the territory of laboratory speculation. Then came the time-lapse observations. Over 4 consecutive nights, the ExoMars cameras measured the green hue increasing in intensity, while the object's overall brightness remained constant. That shouldn't happen. In natural comets, green light spikes when activity increases. When outgassing releases more volatiles. Here, the activity stayed steady while the color deepened, as if the light source was self-modulating rather than reacting to sunlight. It was as though the comet were adjusting its own glow. A secondary puzzle emerged when the Hubble Space Telescope confirmed the same hue but detected subtle flickers, micro-fluctuations in brightness, repeating roughly every 9.7 seconds. That rhythm aligned almost perfectly with the 11-second spectral modulation ESA had logged earlier. 2 instruments, 2 wavelengths, same beat. Coincidence? Possibly, but periodicity is a signature of order, and order is rarely accidental in astrophysics. The simplest natural explanation is rotational modulation, one bright patch of surface-emitting gas as it spins. Yet models show 3I Atlas would have to rotate once every 10 seconds to produce that signal, a speed fast enough to tear a fragile comet apart. If the body had survived such rotation for months, its internal structure couldn't be ice and dust. It would have to be something far stronger. Meanwhile, ground-based astronomers started reporting the same thing the public could now see through large telescopes: an unmistakable emerald haze. Amateur images from Chile, South Africa, and Australia all showed a deepening green envelope with a sharp inner edge, almost like a boundary field. The color gradient didn't fade outward as expected, it stopped abruptly, as if confined by something invisible. ESA's statement tried to temper the excitement. It called the hue a photochemical effect of unusual efficiency, a phrase that managed to say everything and nothing at once. But the numbers didn't lie. The spectral slope, the emission ratios, the boundary cutoff, all pointed to a process that wasn't random. Something was selecting energy bands and maintaining them with precision that nature rarely achieves. Within weeks, independent researchers began testing a daring idea. What if the green glow wasn't emission from gas at all, but reflection from structured material microscopic facets scattering light in a narrow wavelength range, similar to how certain beetle shells or butterfly wings create color without pigment? In biology, it's called structural coloration. In materials science, it's photonic engineering. If that's true, then 3i Atlas isn't glowing, it's communicating. Not in language, but in physics. A modulation of light designed to stand out against the black backdrop of space. So far, no one has confirmed the mechanism. The green coma remains unexplained. Its hue too intense, its boundary too clean, its rhythm too steady. It could still be chemistry. It could be something deeper, something built to be seen from a distance, something that wanted to be noticed. For now, astronomers have renamed it unofficially the Emerald Object, because whatever 3i Atlas is, it's writing its story in green light and daring us to read it. The silence didn't begin with the agencies, it began with the servers. On October 2nd, 2025, NASA's Perseverance rover transmitted its routine batch of images to the Jet Propulsion Laboratory in Pasadena. They appeared on the public raw archive within hours: sky frames, terrain calibration shots, and one peculiar image showing a faint object high in the Martian sky, circled in green by NASA's own processing team. But on the very next sol, the day 3i Atlas reached its closest approach to Mars, the feed stopped. The log file simply jumps from sol 1642 to sol 1644. No images, no metadata, no transmission notes. To the public, it looked like a technical delay. To planetary scientists, it looked impossible. Perseverance's imaging system is automated. Unless the rover is powered down, which it wasn't, the data pipeline cannot simply skip a day. The missing sequence coincides exactly with the window when 7 spacecraft across Mars' orbit and surface were scheduled to observe 3i Atlas. The absence of data wasn't limited to Perseverance. Mars Reconnaissance Orbiter, MRO, the workhorse of NASA's Martian fleet, normally uploads high-resolution images every 48 hours through its HiRISE camera. Those releases stopped after October 2nd as well. The European Space Agency's Mars Express and Trace Gas Orbiter, both of which later confirmed partial observations, also show gaps in their publicly accessible archives for October 3rd and 4th. Even China's Tianwen-1, whose images are typically displayed on state-run science portals, went dark that week. Data silence across multiple independent networks is not coincidence, it's coordination. The first explanation given to journalists was the U.S. government shutdown. More than 15,000 NASA employees were furloughed, and media teams had been told to pause non-essential updates. But those same servers still published Curiosity rover photos, daily atmospheric readings, and calibration maps from Odyssey. So the data infrastructure was functional, just selective. If the loss were truly technical, there would be placeholder logs, checksum reports, or retransmission flags. None appeared. The archive behaves as if the cameras simply didn't operate. But mission planning documents released months earlier show explicit entries labeled Skycam Observation, Interstellar Object 3, I divided by Atlas, Priority 1. The observation was scheduled. The commands were sent. The instruments were ready. Yet the files are gone. Some researchers suggested the downlink windows were missed, but the Deep Space Network records contradict that. Antenna logs from Canberra and Madrid both show successful transmissions from Perseverance during the missing period. Full data packets received, verified, and processed. Whatever was sent, it arrived. The question is what happened after. Normally, once packets reach Earth, they're automatically unpacked and mirrored on public databases within minutes. That process doesn't require a human to approve anything. For the chain to break, someone had to interrupt it manually, either by pulling the data before publication or by flagging it for internal review. Inside the scientific community, people noticed. An astrophysicist at Caltech posted a short message on a private Slack group. "We're missing the most important 24 hours in Martian observation history." Within an hour, the message was deleted. The account went inactive the next day. Then, quietly, a file appeared in a European university's mirror directory, a low-resolution screenshot labeled TGO Composite Temp. It showed a blurred white line cutting diagonally across the black frame. The coordinates matched Mars' orbit on October 3rd. No metadata, no official source, but consistent with a legitimate trace gas orbiter image. Within hours it vanished, replaced by a 404 not found. If the data gap was intentional, the question becomes why. One explanation is benign. The images showed instrument anomalies that needed calibration before public release. But that doesn't explain why no calibration notice or timeline was ever issued. Another, more troubling hypothesis is that something unexpected appeared, something that required interagency consultation before going public. Multiple missions observed the same region simultaneously. If even two of them captured identical irregularities, geometric structure, emission pulses, or anything suggesting non-random formation, the agencies would need to synchronize their statements. That process could take weeks. Meanwhile, silence holds the line. It's now been months, and those missing frames have never been restored. NASA's archive still skips from Sol 1642 to 1644. ESA's metadata remains incomplete. China has never acknowledged the flyby, and when asked in an October press briefing whether additional images of 3I Atlas would be released, a NASA spokesperson responded carefully, "We will share new material once the verification process is complete." Verification of what? No one asked. Sometimes, in planetary science, absence speaks louder than evidence, because if 3I Atlas were nothing more than a comet, there would be no reason for missing data, no need for synchronized silence. But if the instrument saw something that looked organized, something that could not be explained in a single press release, then the easiest response is to remove a day from history. And that's exactly what October 3rd, 2025 has become, a missing day on Mars. When the European Space Agency finally broke the silence, it wasn't with images that answered questions, it was with language designed to avoid them. Their official press release appeared quietly on October 7th, 2025, posted without fanfare on the ESA newsroom site under the modest title, "ExoMars Orbiter Captures Distant Interstellar Visitor." The tone was neutral, the wording clinical, and the photograph's 3 grayscale frames stitched into a simple animation looked utterly ordinary. But for those who know how to read between the lines of institutional language, the subtext was deafening. The first paragraph acknowledged the obvious, that the ExoMars Trace Gas Orbiter had successfully observed 3I divided by Atlas during its close approach to Mars. That phrase, successfully observed, implies the mission achieved its goal. Yet, strangely, the very next sentence contradicted it, stating that the resulting data require weeks or months of analysis before any conclusions can be drawn. In the world of space science, that's an odd pairing. Either an observation is successful and clear, or it's incomplete and uncertain. ESA's statement insisted it was both. Then came the next layer. The object appeared as a slightly fuzzy white dot moving through the frame. That line has since become infamous among astronomers. It's a phrase so plain, so deliberately dull, that it feels scripted to diffuse curiosity. Scientists never describe data like that, not in peer-reviewed papers, not even in early memos. The phrasing echoed a kind of bureaucratic restraint, a tone one uses when the images show more than the institution is ready to admit. Most of the release consisted of technical disclaimers. ESA explained that CASIS, the imaging system, was not optimized for deep space observations, and that the exposures were extraordinarily challenging. That's true, but unnecessary ESA's readers already know that. Including those caveats served a different purpose: preemptive defense. It was a way of saying, if something unusual shows up in these images, it's probably just noise. But the careful language didn't stop there. In one section, ESA described the work of the Mars Express orbiter, noting that it attempted to observe 3I divided by Atlas, though the comet has not yet revealed itself in those images. Not yet revealed is an odd construction. Images are either blank or not. The phrase implies presence, something there but hidden. A scientist might say no detection, below threshold, or inconclusive, not yet revealed. Sounds almost theological. Even more curious was the statement about spectroscopy. It is uncertain whether the coma and tail were bright enough for spectral characterization. Uncertain. That single word drew immediate attention from analysts. When data is missing, agencies say so. When data is clear, they show it. To say it's uncertain whether spectra were obtained at all hints that the data exist, but their contents are problematic. It's the verbal equivalent of a shrug hiding a secret. Reporters looking for clarification reached out to ESA's project scientist, Colin Wilson. His response was equally precise and equally evasive. "It's always extra exciting to see the orbiters responding to unexpected situations," he said. Unexpected situations. 3. IATLAS's path had been known for months. Its flyby geometry was charted down to the minute. Nothing about the timing was unexpected. The only unexpected element could have been what the instruments recorded. In the following days, internal ESA memos leaked to journalists described ongoing data analysis efforts involving stacked imaging, spectral deconvolution, and pattern consistency testing. These are advanced techniques used when the signal is partively weak, or when the signal is too strong in the wrong place. Several sources close to the mission admitted privately that the object's coma showed localized intensity nodes, bright points that repeated across multiple exposures. When one journalist pressed ESA for comment, the agency responded with a short email: "We cannot speculate on subpixel features pending peer review. No speculation, no confirmation." Just the same minimalist script, tight, precise, and impossible to pin down. The true genius of ESA's wording is that it invites interpretation while providing none. Every sentence is technically correct, every detail verifiable, and yet the meaning evaporates on contact. They acknowledged observation without context, detection without description, uncertainty without error. It's the perfect linguistic defense shield. Say enough to look transparent, but never enough to be held accountable. In the weeks since, other agencies have quietly mirrored ESA's tone. NASA's few statements about 3i Atlas borrowed similar phrasing: signal pending analysis, data under review, nominal observation sequence. The Chinese Space Agency used its own version. Preliminary results require refinement. For the public, it reads as bureaucratic delay. For scientists, it reads as choreography. Multiple institutions, each using the same evasive grammar, speaking in a shared dialect of quiet containment. ESA's press release ended with one final line: "The comet continues to be monitored, and further information will be provided once validated." The word validated sounds innocent, but in scientific bureaucracy, validation means permission. It means someone higher up must approve the truth before the truth is spoken. So when historians look back at the discovery of 3i Atlas, they may find that the real breakthrough didn't come from an image or a telescope, but from a single, carefully written paragraph that told the world nothing, because what it really said was, "We saw something. We just don't know how to tell you." When ESA's preliminary compositional data began circulating among partner institutions, it contained one ratio that no one could comfortably explain: strong nickel emission without the expected iron signature. For planetary scientists, that is the spectral equivalent of a red flag waving in the dark. Every comet, asteroid, or dust grain ever analyzed within the solar system carries both metals in a predictable ratio, about 10 atoms of iron for every 1 atom of nickel. That balance traces back to the way elements condensed in the earliest protoplanetary disks. It is one of the most reliable fingerprints of cosmic formation. So when 3i Atlas showed a reversed ratio, the first instinct across every lab was disbelief. The team at the University of Bern recalibrated the spectrometer data twice, thinking a processing offset had swapped wavelength channels. It hadn't. The nickel lines near 341 and 349 nanometers stood tall, clear, and consistent across multiple instruments. The iron lines at 374 and 386 nanometers, normally impossible to miss, were barely detectable, buried in noise. That inversion was real, and it carried consequences far beyond chemistry. The standard model of comet composition relies on inheritance from ancient star debris. Iron dominates because it condenses earlier as dust in cooling nebulae, forming the dense cores of primitive asteroids. Nickel follows, but always as a minority component alloyed with iron. A body rich in nickel and poor in iron cannot form through any process we know inside natural stellar nurseries. That means either our understanding of condensation physics is incomplete, or the object did not form in a normal stellar environment at all. A few scientists tried to fit the anomaly into natural explanations. One idea suggested preferential sublimation. Perhaps the iron was locked deeper within the nucleus, leaving nickel-rich dust to escape first. But at 30 million kilometers from Mars, 3I Atlas was still too cold for deep layer melting. Another proposed that intense cosmic radiation during its interstellar journey had selectively eroded iron compounds on the surface, leaving behind metallic nickel grains more resistant to oxidation. Yet radiation doesn't discriminate so neatly. Over millions of years, it would destroy both metals equally. Then came a more daring theory that the nickel was not free metal at all, but part of ordered alloys or thin film structures capable of reflecting specific wavelengths. In laboratory conditions, nickel-phosphorus coatings and nickel-chromium lattices can produce selective reflectance peaks exactly where ESA saw them. Such coatings are used on satellites and sensor housings to control thermal emission. To imagine them on an interstellar body was almost absurd, yet the match was undeniable. The reflectivity pattern was smoother, sharper, and narrower than rough comet dust could produce. This possibility created quiet discomfort inside ESA. If the surface of 3I Atlas contained manufactured material, or something that behaves like it, then the object's brightness wasn't a natural glow at all. It was engineered albedo. No one was willing to say that publicly, so the official statement chose a safer phrase: enhanced nickel line intensity relative to solar abundance ratios. Enhanced, not reversed, not impossible, just enhanced. Behind the scenes, spectroscopy teams attempted cross-validation using ground-based telescopes. The VLT, in Chile confirmed, elevated nickel lines. The Keck Observatory in Hawaii did too, though its data contained faint hints of titanium and cobalt trace metals that normally accompany industrial alloys, not comets. Every test narrowed the room for coincidence. Nickel is magnetic. It interacts strongly with solar wind particles, and under the right conditions, it can produce electromagnetic oscillations detectable in radio frequencies. Late in October, ESA's Mars Express recorded brief bursts of narrowband static while passing through the region of space that 3I Atlas had crossed days earlier. At first, engineers blamed cosmic interference, but the bursts repeated twice, at identical frequencies matching the nickel spectral line's resonant transitions. To some observers, it looked less like noise and more like a signature, the physical echo of whatever metallic configuration surrounded the nucleus. If these readings are accurate, 3I Atlas may not just contain nickel, it may be using it. In theory, a highly conductive lattice could harness solar induction currents, converting magnetic flux into heat or electrical charge. It would be the simplest and most durable way to power something drifting between stars. Of course, that explanation borders on science fiction, which is why official reports stop well short of suggesting it. The working draft of ESA's second analysis merely states, further modelling is required to determine whether nickel abundance is intrinsic or surface localized. Again, careful words, hiding deeper unease. For now, the nickel without iron problem remains open. No model of stellar formation, no catalogue of comet composition, no simulation of interstellar chemistry can reproduce it. Nature does not build metal frameworks in perfect ratios that mimic technology. But 3I Atlas might have, and until those missing Mars spectra are released, the question stands not whether the data are real, but whether we're ready to accept what they imply. That somewhere, long before we looked up, something else learned to use metal the way we do. For weeks, 3I Atlas had behaved almost predictably. Its light curve, the delicate record of how bright an object appears from Earth, was steady, declining gently as the comet moved farther from Mars. Then, on the night of October 10th, 2025, that calm ended. In less than 3 hours, the magnitude of 3I Atlas increased by nearly 2 full orders of brightness, a jump so abrupt that observatories in Hawaii, Chile, and Australia initially flagged their sensors for malfunction. Comets don't do that, not without a reason. In typical comet physics, brightness changes are slow and graceful. They come from gradual outgassing as solar radiation heats volatile ice beneath the surface. A flare of this magnitude usually signals fragmentation, a piece of the nucleus breaking away and exposing fresh material, but the spectral data didn't match that. The gas emissions stayed constant, and no increase in dust scattering appeared in the days that followed. It wasn't the coma that brightened, it was the core. The first confirmation came from the Las Campanas Observatory in Chile. Their photometric readings showed a sharp vertical spike in the light curve, followed by an equally sudden plateau. It was clean, no oscillations, no tail diffusion, just a perfect ramp-up. The object had grown brighter, then stabilized at the new intensity, as if someone had turned a dimmer switch. That precision made natural explanations harder to sustain. Fragmentation is messy. It leaves debris trails, varying luminosity, asymmetric jets. Here, there was none of that. Within hours, amateur astronomers on social media began posting their own comparisons. Before and after frames from small backyard telescopes showed the change clearly the same patch of stars, but a comet that now burned several magnitudes brighter. No dust outburst, no visible expansion of the coma, just a purified glow, whiter and steadier than before. ESA's first reaction was cautious. They issued a brief note. Preliminary photometry indicates a transient increase in apparent magnitude, possibly due to geometric alignment effects. Alignment effects meaning the object had shifted into a position where sunlight struck it more directly, but this explanation collapsed almost immediately when NASA's Mars Reconnaissance Orbiter registered a similar brightness surge at a completely different angle. Both spacecraft saw the same increase despite observing from opposite sides of Mars's orbit. Whatever caused the flare wasn't geometry, it was intrinsic. A week later, the Hubble Space Telescope added a chilling detail. Spectral readings taken during the brightness peak showed no temperature rise. In normal cometary flares, brightness increases because of heat, sunlight releasing gas that scatters more light. But 3I Atlas's thermal profile didn't change. The infrared emissions remained flat. Something was emitting light without heating up. That phenomenon has a name. Non-thermal radiation. It occurs when energy is released through processes other than heat, like synchrotron radiation in magnetic fields, or electrical discharges along plasma surfaces. Both would be extraordinary in a comet. Yet those were the only options that fit the data. The next clue came not from telescopes but from radio observatories. The Allen Telescope Array in California detected a short, narrow-band pulse, coinciding almost perfectly with the optical flare. The signal was faint, centered near 1.42 GHz. The hydrogen line, often used in deep space communication because it stands out from natural noise. The burst lasted less than 3 seconds and never repeated. Officially, it was logged as a coincidental artifact. Unofficially, researchers at the SETI Institute began cross-correlating it with the ESA light curve. The timing matched within 1/10 of a second. If these events were related, the implications were staggering. It would mean that at the same instant 3I Atlas brightened in visible light, it also emitted a controlled pulse in radio. That's not random physics, that's coordination. Some tried to frame it as a magnetohydrodynamic event, perhaps a sudden alignment of the object's magnetic field with solar wind plasma. That could, in theory, release energy in both optical and radio wavelengths. But such events usually dissipate in minutes, not stabilize into a new luminosity state. 3I Atlas's brightness never returned to baseline. It held steady, brighter, smoother, eerily constant, as though whatever had awakened decided to stay on. By late October, the light curve had become unnervingly flat. The object shone with a fixed magnitude that defied both orbital mechanics and common sense. If it were natural, it would flicker. If it were fragmenting, it would fade. Instead, 3I Atlas sat in the void, burning with mathematical precision. ESA's follow-up memo on October 18th tried to dampen speculation. We caution against overinterpretation of transient photometric events until calibration is complete. Yet one sentence buried deep in the report betrayed their uncertainty. The persistence of post-flare luminosity exceeds expected decay timescales by an order of magnitude. In plain English, it stayed bright far too long. The world's observatories kept watching. But the pattern held. No rotation modulation. No tail expansion. Just steady, impossible light. If comets could talk, this one had just cleared its throat. The sun had been restless for days. Solar observers knew that one of its active regions, AR 3827, a complex web of magnetic loops twisting near the equator, was primed to erupt. On October 4, 2025, it did. A colossal coronal mass ejection, CME, burst outward at nearly 2,000 kilometers per second, hurling billions of tons of magnetized plasma into interplanetary space. For once, Earth wasn't in its path. But something else was. The projected trajectory intersected precisely with the orbit of 3I Atlas, a moving target from another star system. Within hours, models at the Solar and Heliospheric Observatory, SOHO, and NASA's Stereo A spacecraft confirmed what no one expected. The ejected plasma cloud would collide almost head-on with the interstellar object within 72 hours. For ordinary comets, this would be catastrophic. CME impacts strip away tails, ionize comas, and sometimes tear entire nuclei apart. Yet as soon as analysts plugged in 3I Atlas's parameters, the equations stopped behaving. The models refused to stabilize. A comet's response to a CME can be predicted if you know three things: its size, its density, and its composition. For 3I Atlas, none of those were certain. ESA's earlier data suggested a dense, possibly metallic core wrapped in volatile ices. That meant it might react less like a fragile snowball and more like a conductor, an object capable of generating induced currents as the CME's magnetic field swept across it. The idea unsettled physicists. If the body could hold charge, the approaching solar storm wasn't just a hazard, it was an experiment waiting to happen. ESA's Space Weather Coordination Center ran 3 predictive models. The first assumed a normal comet composition. The CME would strip the ion tail and produce a short-lived brightness surge before the nucleus stabilized. The second model treated the object as a compact, high-density asteroid, predicting minor surface ablation and no observable flare. The third scenario, a speculative one inserted by a researcher whose name was later redacted, considered what would happen if 3I Atlas had metallic conductivity. In that case, the passing plasma could generate immense electromagnetic tension, possibly igniting local discharges or even coherent radio emission. That last prediction wasn't included in the public summary, but it was the one that circulated most quietly among mission scientists. Because if it was correct, the CME impact could act as a kind of activation, pulse the largest natural electromagnetic event in the inner solar system, directed precisely at the most anomalous object ever recorded. On October 5th, ESA issued a routine solar weather bulletin. Buried in the middle was one line: Coordinated observation of interstellar object 3, I divided by Atlas, will continue during solar event interaction. Brightness variations expected. The statement read like background noise, but internally, teams were mobilizing. The Hubble Space Telescope, Mars Express, and even the James Webb Space Telescope were scheduled for synchronized observation windows spanning October 6th through 7th. The event had become a global experiment conducted in real time. For scientists, the CME impact was an opportunity to test theories that bordered on science fiction. Could a comet behave like an antenna? Could metallic dust within its coma channel current? Could we, even briefly, watch solar plasma interacting with something not entirely natural? At 14 UTC on October 6th, the leading edge of the CME was predicted to reach the region of space containing 3I Atlas. As the countdown approached, observatories from Spain to South Africa prepared for live spectrographic recording. One researcher compared it to waiting for thunder after seeing lightning. The first solar particles would hit hours before the magnetic wavefront, producing a cascade of ionization as electrons stripped from the comet's gases. If the object behaved normally, its coma would expand violently, glow bluish-white, and lose structure. But if it didn't, if it absorbed, redirected, or synchronized with the incoming field, then we were looking at an entirely new category of astrophysical behavior. Predictions became a matter of belief more than science. Some solar physicists warned that the CME might disintegrate the nucleus. Others whispered that it might awaken it. A few called it a cosmic accident, a perfect stress test delivered by the sun itself. Hours before the predicted impact, a flare of secondary radiation swept across the inner solar system, harmless to satellites, but visible on magnetometers as a sharp spike. Then came the waiting. Ground telescopes lost view behind the sun's glare. Only orbiters positioned around Mars and the inner heliosphere could see what happened next. And then, Silence. Data blackout. No live updates. No brightness reports. ESA promised to release results after calibration, but days later, the only official statement read, "Preliminary analysis indicates significant interaction between solar ejecta and 3I divided by Atlas. Full characterization pending." That single phrase, significant interaction, was all the world got. But for those who read the classified side of the report, the graphs told another story. Energy spikes that didn't decay, light curves that rose and flattened instead of fading. It was as if the comet had taken the full blow of the sun and not only survived but responded. The sun had screamed, and something out there had screamed back. The solar storm that collided with 3I Atlas on October 6, 2025, should have ended the mystery. A direct hit from a coronal mass ejection that powerful typically shreds fragile comets into vapor. Instead, it revealed something no one expected. Structure. When the solar plasma reached the region of space surrounding 3I Atlas, the ExoMars Trace Gas Orbiter and Mars Express recorded a faint but consistent pattern in the scattered light, a pattern that repeated across multiple instruments and wavelengths. To most observers, it looked like interference fringes, the kind you'd expect from waves diffracting around a solid object. But these weren't static. They shifted rhythmically, like the pulse of a mechanical heartbeat. At first, the explanation was simple. Magnetic lensing. When a charged plasma passes a metallic or ionized surface, it can create symmetrical patterns. The trouble was, the symmetry here wasn't radial. As with a sphere, it was polygonal. The reflected emissions formed angular nodes, almost hexagonal, each point glowing faintly before fading in perfect sequence. That geometry doesn't appear in nature. It suggested boundaries, orientation, and possibly intent. ESA's imaging division didn't publish those early light maps. Instead, they issued a cautious note about data artifacts produced by dynamic plasma fields. But among the raw telemetry, leaked from the Solar and Heliospheric Observatory, SOHO, independent analysts noticed identical modulation signatures, oscillations, in the 8 to 12-second range, perfectly in sync with the rotational pulse previously detected in the green coma. In other words, the same rhythm that had defined the object's optical flicker was now visible in its electromagnetic echo. This was the moment when a few scientists began whispering a word that hadn't been used in serious astronomy since the days of Oumuamua: geometry. Because if an object reacts to radiation with symmetry, it's not just reflecting, it's resonating. Radiation meeting geometry means more than light bouncing off surfaces. It means energy interacting with form, as if the shape itself determines the response. Engineers on Earth use this principle in antenna design, specific curves and panels tuned to capture or redirect electromagnetic fields. To see similar precision in something the size of a small mountain drifting between planets was unsettling. ESA's internal simulations tried to replicate the interference pattern using natural models. They assumed uneven outgassing jets, surface ridges, dust ejection streams, but none could reproduce the timing or angular uniformity. Only a faceted geometry, something with planes or edges, created the observed sequence. Yet the coma surrounding 3I Atlas should have blurred any such pattern entirely. That meant either the coma had cleared for a few seconds impossibly fast, or the radiation had penetrated the gas and interacted directly with something underneath it. At the European Space Operations Centre, a team led by Colin Wilson ran a radiative transfer model using hypothetical internal scaffolding, a lattice of reflective material inside a thin dust shell. The model fit the data perfectly: the reflection patterns, the steady rhythm, the unchanged thermal output, all aligned if the structure beneath the coma wasn't solid rock but a hollow grid, possibly metallic, responding to the CME like a resonant cage. Of course, none of that appeared in the official communiques. The phrase ESA used was characteristically careful. Localized coherence in post-CME photometric response, consistent with transient structural alignment of ionized dust fields. In plain English, it looked organized. But ESA wouldn't call it that. Meanwhile, radio telescopes continued picking up narrowband fluctuations near the hydrogen frequency that first appeared during the brightness flare. The pulses now followed a clearer pattern bursts, grouped in threes, separated by the same 9-second rhythm recorded in optical light. That synchronization between light and radio energy hinted that the structure wasn't just reflecting, it was modulating. Radiation had met geometry, and geometry was answering back. At this stage, a new theoretical branch emerged in internal discussions, what some called the resonant vessel hypothesis. It suggested that 3I Atlas might be more than a solid body. It could be an electromagnetic resonator, designed whether by nature or by something else, to harness stellar radiation and re-emit it in controlled frequencies. In essence, a cosmic machine built not to travel fast but to survive forever by feeding on starlight. Officially, no agency has endorsed that theory. But the data remain. Hexagonal emission nodes, synchronized pulses, constant brightness despite radiation bombardment. A natural comet absorbs and disintegrates under solar wind. 3I Atlas absorbed and responded. ESA's last internal update before the object passed behind the Sun contained one line that has since become legend among those who saw it. Spectral coherence persists. Structure not ruled out, because on that October night, humanity witnessed something new in the physics of light. For the first time, radiation didn't just illuminate an interstellar traveler, it revealed the shape of something that may have been waiting for the right kind of storm to be seen. When ESA scientists realized that 3I Atlas's coma was too faint to reveal structure in single frames, they turned to a method astronomers often use to detect extremely dim objects: image stacking. It's a simple idea: take multiple exposures of the same region, align them precisely, and add them together so that real signals amplify while random noise cancels out. In theory, this would help bring out the comet's faint halo or tail. In practice, it revealed something far stranger. The experiment began on October 8, 2025, 2 days after the CME impact, when Mars Express had completed 47 passes with the high-resolution stereo camera, HRSC. Each pass captured the same portion of space where 3I Atlas had appeared earlier in the week. The raw images showed nothing but faint background stars. Yet when technicians at ESA's data center in Darmstadt stacked the first 20 exposures, a shape emerged barely visible, but distinct enough to notice. It wasn't round. The composite frame showed an elongated hexagon, brighter along its edges than at its center, tilted at a slight angle relative to the solar plane. At first, the team assumed misalignment. They tried again, correcting for spacecraft drift and camera distortion. The shape didn't disappear. It became sharper. The brightness pattern repeated identically in all 3 RGB channels, meaning it wasn't a processing error or color artifact. It was real light, arriving from a geometric source. For 3 days, ESA repeated the process using independent datasets: ExoMars TGO's Cassis camera, Mars Express HRSC, and even archived stereo A heliospheric imager data. Every set, when stacked, produced the same angular echo, a 6-pointed frame glowing faintly within the surrounding haze. And every time, the signal-to-noise ratio improved beyond what physics predicted for random noise accumulation. Normally, stacking yields a gain proportional to the square root of the number of frames. Here, the gain was exponential. Each layer made the image disproportionately clearer, as if the object itself were reinforcing the pattern responding to observation. By October 12th, the ESA team had accumulated over 150 frames. When combined, they formed what looked unmistakably like a structured projection, a hexagonal shell enclosing a dim central nucleus. The leading theory was diffraction. Perhaps the coma's particles had aligned under electromagnetic stress during the CME, creating a transient crystalline field. But no known plasma dynamic can hold symmetry that stable for days. It should have collapsed instantly once the solar wind passed. Instead, the pattern persisted. When the images were reviewed by the European Southern Observatory in Chile, a second anomaly appeared. The hexagon's edges weren't diffuse. As you'd expect from dust scattering, they were sharp, pixel-level sharp, implying either solid boundaries or coherent light. Spectral overlays showed mild polarization consistent with metallic reflection, not gaseous emission. One scientist quietly labeled the file Atlas, Structure, Candidate. It was never intended for release. Then came the unexpected feedback. When the stacked sequence was processed through an adaptive deconvolution algorithm, an AI tool normally used to clean telescope blur, the software began enhancing faint secondary lines running inside the hexagon. They converged toward the center like struts or spokes. The AI flagged them as non-random alignment features, with confidence above 98%. The analysis was stopped, the file locked, and the experiment archived under restricted access. The official ESA report summarized the entire process in one line. Multiple image integrations produced ambiguous geometric artifacts. Subsequent investigation deferred. That phrase, ambiguous geometric artifacts, became infamous in astronomy forums, because for those who saw the leaked composites before they vanished from servers, ambiguity was the last word anyone would use. Outside ESA, independent astrophotographers attempted their own stacking with publicly released frames. They too saw the same pattern. Though weaker, a faint symmetry invisible in single exposures but undeniable when dozens were combined. Forums lit up with speculation. Was it coincidence? Or had ESA's stacked imaging accidentally uncovered the skeleton of an engineered body cloaked by dust? The debate split the community. Traditionalists argued that human perception sees patterns in noise. Others countered with math the repeating pixel geometry, the reproducible ratios, the statistical impossibility of random alignment across multiple instruments. When one independent analyst overlaid the stacked pattern with known structural forms from aerospace engineering antenna, arrays, field resonators, solar sails, the match was uncomfortably close. ESA's silence only amplified the intrigue. No retraction, no clarification, no replacement data, just a quiet deletion of the highest gain composites from their image server, and a statement about continuing data verification, but whispers inside the agency told a different story. According to an internal memo later leaked to a German science journalist, the stacked experiment wasn't halted because it failed, but because the last iterations began showing movement. The hexagonal pattern wasn't static. It shifted orientation between frames, subtly realigning as though tracking the sunday. If that's true, then stacking didn't just reveal geometry. It revealed behavior. And for the scientists who saw those last images before they disappeared, the implications were clear. They weren't looking at noise. They were looking at something that didn't want to remain hidden. Something using geometry, not as structure, but as signal. For months, astronomers had been watching a blur, a softly glowing envelope of dust and vapor drifting through the inner solar system. 3I Atlas, they said, was a comet. An interstellar one, yes, but still a comet. Until October 14th, 2025, when a faint, flickering darkness appeared inside its own light. The anomaly was first spotted by a research team at the Lowell Observatory in Arizona, who were testing a new high-dynamic range filter on archived ESA imagery. By pushing exposure contrast far beyond normal calibration limits, they hoped to tease out fine gradients inside the coma. Instead, they found shadows. At first, it made no sense comets don't cast shadows within themselves. Their light comes from sunlight scattered by dust. Every particle glows uniformly, but the data showed sharp dips in luminosity, not smooth fall-offs. When the same region was cross-checked with images from Mars Express, the same pattern emerged, streaks of lower intensity running diagonally beneath the main glow, forming what looked like struts or silhouettes. They didn't move with the comet's rotation. They moved independently. The term shadows beneath the coma appeared in an internal memo a day later, circulated between ESA's photometric analysis divisions. It described localized attenuation zones, inconsistent with natural density gradients. In plain English, the darkness had shape. The brightest part of the coma seemed to fold around something opaque, like light bending around a solid form, but no solid object was visible. The breakthrough came when engineers used a polarimetric inversion, a technique that reconstructs three-dimensional scattering surfaces from polarized light. The model that emerged was uncanny. Inside the diffuse coma was a region roughly 12 kilometers wide, hexagonal in cross-section, with flat reflectivity profiles at angles too precise to be random. The outer coma wrapped around this invisible frame like mist around glass. ESA never released the render, but one analyst, speaking anonymously, described it years later. It looked like a hollow prism suspended in dust. When sunlight refracts through gas, it spreads into smooth gradients. When it refracts through geometry, it produces shadows with clean edges. And these edges were crisp. They cut through the soft coma light in ways no random plume could produce. Some sections even appeared to occlude starlight behind the object, another impossibility, unless something solid was there to block it. If this structure existed, it shouldn't have survived. The CME that struck 3I Atlas days earlier should have shredded any fragile form, yet the shadows remained, unshaken, as though anchored within an internal framework. Scientists began whispering about electromagnetic confinement, a process where charged plasma could be held in shape by magnetic fields. But that would require a sustained intelligent configuration and an energy source. The phenomenon deepened when infrared data arrived from the James Webb Space Telescope. The region corresponding to the shadowed area was colder than its surroundings, about 20 Kelvin lower. That inversion violated thermodynamic expectations. It suggested active regulation heat being absorbed, not emitted. To some, it looked like shielding. ESA's official response was predictably careful. Observed substructure within coma may represent transient dust depletion zones, but internal notes tell a different story. A private briefing from October 17th described the anomaly as stable across rotational frames, potentially structural. Meanwhile, amateur astrophotographers began to notice something odd in their own images. When they increased contrast, they too saw faint bands of darkness near the comet's core. Not artifacts, but faint, repeating shadows that persisted night after night. Crowdsourced data from telescopes in Japan, Chile, and South Africa confirmed that the darker zones were real and geometric. Then came the strangest discovery of all. During one observation window, the shadows shifted, not randomly, but in unison. Over the course of 18 minutes, they rotated by roughly 12 degrees, aligning perfectly with the solar vector. To the naked eye, 3I Atlas hadn't moved, but the shadows had adjusted themselves, as if following the Sunday. ESA quietly removed several datasets from public access the next morning. No explanation, just silence. For those few scientists who still had access to the raw telemetry, one conclusion became impossible to avoid. The coma wasn't hiding something. It was built around something, a core with planar surfaces, capable of regulating light and heat, moving in response to solar geometry. In the soft green glow that once looked like dust, we were seeing a mask, a luminous veil concealing structure, one that reacted, adapted, and perhaps even protected whatever lay beneath. 3. Atlas wasn't just glowing anymore. It was casting its own shadows. Every comet has its moment of truth. It comes at perihelion, the point of closest approach to the sun, where heat, pressure, and radiation reach levels no object can ignore. For 3I Atlas, that moment arrived on October 21st, 2025, just as the world's attention had begun to drift elsewhere. But to the handful of scientists still watching, this was the experiment the universe had arranged for them, a natural stress test, one no agency could engineer, one that would either prove 3I Atlas was ordinary matter or confirm that it was something unprecedented. ESA's predictive models had been cautious. If the object behaved like a comet, it would erupt spectacularly, venting gas and dust as volatile ices sublimated under solar heat. Its coma should expand, its brightness should spike, and within days it would begin to fragment. That's how comets die. But 3I Atlas refused to die. As the object drew within 0.7 astronomical units of the Sun, closer than Venus, the solar orbiter spacecraft positioned on the sunward side began continuous imaging. The feed, meant for open release, suddenly went offline 30 minutes after the object entered field of view. When it returned, 3 hours later, the data stream had gaps, missing timestamps, corrupted frames, incomplete telemetry. But within those frames, analysts later reconstructed something impossible. No increase in thermal emission. Every comet brightens exponentially as it nears the sun. Even a small one can double its apparent brightness each day. 3I Atlas did the opposite. Its visual magnitude dipped slightly, then plateaued, as if it were absorbing energy rather than reflecting it. More puzzling still, spectral readings flattened the green coma that had dominated the previous weeks, dulled toward white, and then toward a pale metallic grey. From Earth, observers noticed a brief halo flare, one flash of light that lasted less than a second. It wasn't solar reflection. It was a directional burst, bright enough to saturate detectors in Chile, Japan, and the Canary Islands. The timing corresponded exactly with perihelion passage, 1342 UTC. Some described it as a glint, others as a pulse, but the brightness curve had no thermal tail, no heat, no residual dust, no plume, just a single flash, uniform and instantaneous, like a signal. Then came the strangest part. As the object passed behind the Sun from Earth's perspective, it should have become invisible for at least 10 days. But on October 24th, 3 days into the blackout, NASA's Stereo-A spacecraft caught a faint but distinct reflection in the region where 3I Atlas should have been completely obscured. The reflection wasn't light from the Sunday, it was light to the Sun. A thin beam directed inward, like a line of feedback in a mirror system. No one could explain it. ESA's internal memo from that week used deliberately vague language: unexpected attenuation in expected solar scattering, potential non-thermal behavior under extreme flux conditions. In less coded terms, the object didn't scatter sunlight, it handled it. Some speculated it was using the Sun's energy to adjust course, perhaps through magnetic coupling. Others believed the comet's dissipation had exposed a surface capable of controlled reflection, the kind of precision you'd see in adaptive optics or solar sails. By October 28th, when 3I Atlas finally re-emerged from behind the Sun, it was unchanged. No fragmentation, no debris, no expansion of its coma. It looked cleaner, sharper, and more stable than before, as if the encounter had refined it. The coma had shrunk by almost half, its once chaotic edges now forming a subtle but symmetrical boundary. For the first time since discovery, the object appeared to be intact by choice. Among scientists, this moment became known as the perihelion test. It was the universe's most extreme examination, and 3I Atlas passed flawlessly. Every natural model failed. Its temperature remained constant. Its albedo increased slightly, implying surface renewal. And though it endured temperatures exceeding 700 degrees Celsius, not a trace of sublimation appeared in spectra. ESA's official statement concluded blandly: no anomalous behavior observed. But inside the private research channels, one short line of text circulated quietly between physicists, astronomers, and engineers who had been following the object for months. It didn't survive perihelion, it adapted to it. As seconder, the Sun, our most destructive testing ground, had thrown everything it had at an interstellar visitor. Instead of breaking, the visitor absorbed, adjusted, and emerged stronger. Whether that meant self-regulation, shielding, or something deeper remains unknown. But for those who saw the raw data, one conclusion was unavoidable. 3I Atlas had just demonstrated resilience no natural comet could ever achieve. And from that day on, the question haunting every agency wasn't what it was made of. It was what it was built for. By late October 2025, 3I Atlas had passed perihelion and begun its slow outbound drift toward the cold. To the public, the story was fading. But within a handful of mission control rooms scattered across 3 continents, the real work had only just begun. 7 orbiters, each with its own sensors, its own angles, and its own secrets, had seen something that didn't fit. And though every agency wrote different reports, the tone of those reports was eerily identical. Controlled restraint. The Mars Reconnaissance Orbiter, MRO, was the first to whisper. Its high-resolution high-rise camera, designed to photograph boulders and dust devils, had captured streaks of light near the edge of its field of view during 3I Atlas's flyby. When analysts overlaid the frames, they found that the streaks formed parallel lines, each exactly 65 kilometers apart, 2 uniform for debris, 2 linear for plasma. The internal caption read, "Unidentified collimated emissions." NASA's public summary called them imaging artifacts, but the brightness pattern repeated over 12 consecutive orbits. Artifacts don't repeat in formation. Meanwhile, Mars Odyssey's Themis instrument recorded inexplicable heat signatures in the thin upper atmosphere. Short, sharp pulses of infrared energy appeared roughly every 9 seconds, the same rhythm already documented in optical and radio data. The pulses originated not from the comet, but from the space directly between Mars and 3I Atlas, as though energy were transferring through invisible channels. Engineers described it as Thermal blooming without source. The phrase was redacted from the final archive copy. ESA's Mars Express observed something subtler but stranger. During its final imaging passes, its magnetometer detected microfluctuations in the local field strength, tiny ripples that synchronized perfectly with the comet's changing brightness. The readings suggested that 3I Atlas wasn't merely illuminated by the sun, it was interacting with it, bending magnetic lines like a metallic object in a magnetic storm. When the analysis team simulated possible causes, only one matched the pattern: a conductive shell rotating within a controlled magnetic envelope. They didn't publish that. Instead, the official note read, "Transient field distortion likely related to solar wind variability." Across the planet, China's Tianwen-1 orbiter, usually prolific with images, released nothing at all. But a month later, during a routine systems update, Chinese telemetry leaked into an open academic database for less than 2 hours before being pulled. In that brief window, analysts in Europe grabbed a single log entry. Specular reflection observed. Duration 0.3 seconds. Specular means mirror-like. Something near Mars had reflected sunlight so precisely that it produced a glare stronger than Tianwen-1's onboard sensors could process. For a fragment of a second, the object shone like polished metal. The UAE's Hope orbiter, positioned farther out, carried an infrared spectrometer tuned for atmospheric gases. It detected none. Instead, its sensors registered periodic null zones intervals of total signal loss that occurred every 9 seconds, matching the same beat noted elsewhere. Onboard diagnostics confirmed no fault. The nulls were external, as if a pulse of energy were briefly blinding the instrument with perfect regularity. Individually, each anomaly could be dismissed. Together, they formed a single pattern. Precision. The same interval, the same synchronization, the same avoidance of noise. At the European Space Operations Center, mission controllers pieced the data into a timeline. They didn't have enough to see the object directly, but they could infer its behavior. Between October 6th and 21st, 3I Atlas had responded to every solar event: the CME, the radiation spikes, the perihelion heat in phase with incoming flux. Not as a passive body being struck, but as a system reacting. One engineer compared it to a leaf that adjusts itself in the wind, not to resist, but to ride it. And when ESA circulated their combined report to partner agencies on November 2nd, it contained a single summary line: object displays coherence across electromagnetic spectrum inconsistent with stochastic natural processes. That sentence never appeared in the public version. What the orbiters know, and what we were never told, is that 3I Atlas wasn't drifting. It was aligning, matching its internal rhythm to solar rhythm, syncing its field to ours. The data points weren't noise. They were coordination. If comets are nature's wanderers, then 3I Atlas was something else entirely. It was a listener, and as the orbiters turned their cameras away, one final transmission from Mars reconnaissance quietly slipped through an unfiltered channel, a note so brief it could have been dismissed as telemetry code. Signal stable, pattern repeating, object adapting. By the end of October 2025, 3I Atlas had already passed beyond Mars and begun to fade into the outer darkness, shrinking into the same quiet it arrived from. The agencies stopped talking. The news cycle moved on. The databases remained redacted. But the data, those small, persistent anomalies, never went away. What was left behind wasn't an answer, but a pattern. A visitor that reflected sunlight without heating up, that produced symmetry inside chaos, that passed through a solar storm without disintegrating, and that changed brightness as if obeying rhythm rather than physics. Everything we saw, from the green coma to the shadows beneath it, spoke not of coincidence, but of design. And yet no one, not NASA, not ESA, not China, has dared to call it that. Maybe they can't, because if you name it, you must also admit what it means. That we were watched not from light years away, but from inside our own solar system. When the final composite frames from the solar orbiter were decrypted weeks later, they showed something subtle, almost poetic. The object didn't leave a trail of debris like every comet before it. It left a faint wake of ordered dust, arranged in repeating intervals, like a breadcrumb trail of geometry dissolving into space. A perfect hexagon fading into the void. That was the last signal we ever saw from 3I Atlas. No explosion, No collapse. Just silence again. But this time, silence felt intentional. Maybe that's the real verdict. That the universe doesn't shout when it wants to be understood. It whispers and waits to see who's listening. So, what do we do with that? We keep watching. We keep questioning. Because someday soon, when another interstellar visitor drifts through the light of our sun, we'll remember this one, the object that defied heat, gravity, and probability, and we'll know what to look for. Not the noise, not the data, but the pattern hiding underneath it. If you followed this story all the way to the end, thank you for being one of the few who still listens for the quiet things. Like, subscribe, and tell me where you're watching from and what time it is there. Because time, in this story, is the only thing that's truly universal. And remember, the sky forgets nothing.